First part of today's activities are going to be reviewing for exam number 5 on atomic structure and periodicity. And I'm working from the review document, and I picked out some that are representative. So, sooner we get done with this, the sooner we can do our lab. Number 2 and 3. Which form of electromagnetic radiation has the longest wavelengths? You remember your continuum where we have visible here? And then on this side, we have I think the longer ones. So this is going to be the red end, this is going to be the blue end. This will be infrared. And then we'll have pretty wide microwave. And then radio waves out here. On this side, we have ultraviolet. Then we have X-ray, I think. And way down here we have, actually X-ray extends further than that. Then we have gamma ray. See, I can do a better job than that. Trying to use the Greek letter for gamma. Gamma ray. Okay. Wavelengths increase in this direction. The longer wavelengths are on this end. So since speed of light equals frequency times wavelength, they're inversely proportional. As this one gets bigger, the frequency gets smaller. So the frequency will increase this direction. They opposite to one another. Okay. So to answer the question, the longest wavelength is on this end. Let's see what we got to choose from. Microwave, radio waves. There you go. Radio. Okay. Which of the following frequencies corresponds to light with the longest wavelength? All right, so the frequencies with the longest wavelength are down here. The smallest value of frequencies will give you the longest wavelength. So I would look at the powers of 10 first, and then only look at the coefficient if you need to break a tie. So let's see, we got 13, 5, 20, 12, 9. 5 seems to be the smallest one, 10 to the 5th. So that would correspond to the longest wavelength, B. Okay. Let's see if I need to keep that up there. I'll just leave it for a little bit. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. So let's see, this is 6. If it's 254 nanometers, that's just one of the lines from the mercury spectrum. When mercury emits a photon of light at this wavelength, the frequency of this light is. Right, so all we need to do is use that formula. Right? If C equals frequency times wavelength, then frequency equals C divided by wavelength. Remember what the speed of light is? 9979 times 10 to the 8 meters per second. These have to be in SI units. That's not SI units. Right? Nanometers. What's a nano? 10 to the minus 9th. So it's 254 times 10 to the minus 9th meters. And calculators will accept it that way. You don't have to convert it to scientific notation. Just exponential is fine. So we could put it into our calculator just like this. And that'll cancel the meters and put seconds in the denominator, and that's where it needs to be for frequency. Right, reciprocal seconds or cycles per second. It's frequency. And if we do our calculations correctly, we should come out with 1.18 times 10 to the minus 15. No, 10 plus 15 reciprocal seconds or hertz. It's another unit of measure, which is exactly the same numerically as reciprocal seconds. Okay. And let's see. Let's erase that so we can. So I don't have to erase that one. We'll not need that one again. 2, 3, 6. That unit change is a trap for some students. If you forget to change the units, then your answer will not come out right. The wily creator of some multiple choice questions might do that calculation the way the student would do it wrong and put that answer in there. So you might find your answer in there, but it's the wrong one. Okay, number 8. Green light can have a wavelength of 543 nanometers. I like the wording there. Can have a wavelength of 543. It's possible that green, to our eyes, can have several wavelengths that are close to that. That's one of them. The energy of a photon of this light is. Okay, so what we're going for now is Planck's equation. Planck's constant times frequency. Or if we transform this equation to frequency, then we get C over lambda, and that would be E H C over lambda. Okay. So now, well, we also need to change this to meters. 543 times 10 to the minus 9 meters. Planck's constant, I think I remember, 6.626 times 10 to the minus 34 joule seconds. And then speed of light hasn't changed since we used it last. In the 8th meters per second. And wavelength is 543 times 10 to the minus 9 meters. And the energy should be in joules. Right? Meters cancel, joules is in the denominator, seconds is in the denominator, seconds in the numerator, they cancel. And leaves us with joule, so we're good. And if we do the calculations correctly, we should end up with 3.66 times 10 to the minus 19 joules for that photon of light. Number 11. How many of the following are correct? Oh, I, double I, triple I, and IB. That's it. Okay. So let's see. Statement 1, the importance of the equation E equals mc squared is that energy has mass. Yeah, it equates energy with mass. So this one's correct. Electromagnetic radiation can be thought of as a stream of particles called photons. Yep. That's true. Electromagnetic radiation exhibits wave properties. It does that too. It's both wave and particle. Energy can only occur in discrete units called quanta. That's also true. Right, so all of them are true. All right, 12, 13, 14, and 15 are based upon this table. All right, let me make some room here. Well, 13, 15. All right. Electrons have wave properties. Oh, what's the significance of the table? From the following list of observations, choose the one that most clearly supports the conclusion of the following 4 questions. Okay, so the conclusion that electrons have wave properties is derived from one of these, A through E. Emission spectrum of hydrogen? No. I mean, that doesn't prove wave properties. What we were looking for is a phenomenon of matter that says this has to be waves. Emission spectrum, no, that's more discrete energy particles, photons. Photoelectric effect, that's definitely photons. Right. Scattering of alpha particles by metal foil, I don't know what that has to do with anything. Well, according to Rutherford, it proves that the existence of the nuclear atom. Diffraction. That looks like a good candidate. What is diffraction? I could do this 2 different ways. One is to use a slit right here, like a slit in that barrier. And you got a wave coming in. And when it hits that slit, that serves as a point source for a new wave that propagates out like that. That's a property of waves, diffraction. So D is probably the best answer for 12. Cathode rays are actually electrons. So that wouldn't be it. Electromagnetic radiation has wave characteristics. Well, we're talking about diffraction again. Whoa. Cloudburst. Electrons and atoms have quantized energies. Okay, so which one speaks to that one? The emission spectrum. Quantized energies of electrons means that they can only move from this energy level to that one or vice versa, and nothing in between. That's why you get a line spectrum and not a continuous spectrum. If electrons could move anywhere they wanted to around an atom, you'd get a white continuous spectrum for every element in the periodic table. But you get discrete line spectra, and that's because energy is quantized. So A is for 14. Guess I'm gonna have to speak up. Kind of noisy.
Easy. Just out of nowhere.
15. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. All right, the key there is wavelength. And we didn't talk about this. And if you stick around for the 2nd semester, we're going to actually do calculations with this type of crystallography. Now you can use 2 different methods. The method that we're going to use in the 2nd semester uses X-rays. So that's definitely waves. But electrons can also exhibit wave properties, according to de Broglie. And we didn't talk about this much in the lecture, but de Broglie proposed that based upon Einstein's theory, that matter and energy are equivalent. He says, well, matter should be able to have wave properties in that case, right? So he took Einstein's equation. That, and he took Planck's equation, which incorporates some wave characteristics, H, like that, and he equated the two, right? And let's see, let's solve it for, well, actually, he didn't just take Einstein's equation. He said, if you're talking about other, not light, but you're talking about subatomic particles, for instance, then this would become v squared, their velocity. In which case we would say, let's see, let's solve it for frequency. So if these two are equal, that means mass times velocity squared equals Planck's constant times frequency. And if we solve it for frequency, like that, then we have mass, v squared over Planck's constant. Okay. So if you know the velocity of, say, an electron, we know the mass of the electron, then we can calculate what its equivalent frequency would be. Or if we can measure its wavelength and convert that to frequency and how fast it's going, then we can equate that to its mass. That's de Broglie's equation. Okay, so to answer the question is, the spacing between a crystal is on the order of de Broglie wavelength of accelerated electrons. Well, the giveaway there is wavelength. And the only thing that speaks to wavelength in that list is diffraction. So that's also D. We use this characteristic in electron microscopes because that gives them a much lower diffraction limit, and they can discern the differences between two positions or particles in a target with a smaller wavelength. So electron microscope can resolve things down to, oh, I don't know. Well, they can magnify up to several 100,000 times, whereas a light microscope, you're doing good to get 1,000 times. Some light microscopes can go below that. They take special techniques and using only certain types of light, short wavelengths. Okay, so moving on. 16. I'm going to leave that there because I think we're going to use it to solve another problem later on. The 4 lines observed in the visible spectrum, emission spectrum of hydrogen tell us that what? The hydrogen molecule came from, has the formula H4. I'd like to see that. An H4 molecule. I don't think so. We could observe more lines if we had a stronger prism. That's been tried. In fact, a prism, the emission spectrum of hydrogen, was placed in the beam of hydrogen. Actually, it was deuterium. Let's see, one. Yes. And if you get the spectrum like this, then it's going to split into four wavelengths, visible wavelengths. And then you take another prism and put it right here, and one there, and one there, and one there. And what do you get? You get a single line. So it didn't split anymore. So that doesn't work. B is false. There are 4 electrons in an excited hydrogen atom. That'd be neat. How do you get 4 electrons? Well, of course, it'd be a 3 plus charge. But that's not why you see those emission spectra. Only certain energies are allowed for the electron in a hydrogen atom. That's the indicator. This 4-line spectrum indicates that quantized nature of electron movement in the hydrogen atom. Spectrum's not continuous. We just said it was a line spectrum, so D is the answer. Okay, 17? Yeah, 17. For which of the following transitions does the light emitted have the longest wavelength? Okay, I equate the longest wavelength with the lowest energy. According to Planck's equation, this relationship also means energy. As frequency increases, energy increases. That means that as wavelength increases, energy decreases for the photons. So for the longest wavelength, you want the lowest energy, which means the shortest jump for the electron. Right? So if you get your representation of your atom, you have 1 here, 2 is way out here, and then 3 gets closer, 4 gets even closer. We got any more? That's it. Okay. So if you jump from 2 to 1, that's a pretty big jump. If you 3 to 1, 4 to 1, anything to 1 is going to be a pretty big jump. So C and E are probably not it. So what else do we have? 4 to 3, 4 to 2, and 3 to 2. 3 to 2 is going to be this jump. 4 to 3 is going to be a smaller jump. And 4 to 2 is going to be a bigger jump. So the smallest jump of these is this one. 4 to 3 will give you the lowest energy, longest wavelength. Okay. Oh, that's why A is the answer.
Studying for looking at all the questions, I actually found a really good website that had a chart of first layer up through like the 4th layer. I used that to kind of reference as I went through and trying it out, doing the questions and checking my answer.
What kind of chart did it have?
I just checked.
Was it like a model of the atom?
It was like a university article about quantum mechanics
Oh,
that had the data I needed.
so this one should be. Oh, I haven't got to that one yet. This is 8 there. And 18. When a hydrogen electron makes a transition from 3 to 1, which of the following statements is true? When it goes from 3 to 1, it's going from high energy to lower energy, which means it has to emit radiation. So it could be 1. Yeah, 1's a good answer. It emits radiation. 1 and 2 can't be there at the same time. The electron loses energy. Yeah. It loses energy by giving it up to a photon of light. And then the electron cannot make this transition. Well, that's a dumb answer. So 1 and 3, B, would be our best answer for this one. We go to 21. Which of the following is incorrect? All right, let's see. We don't have any wonky ones in like 2 of the above and none of the above. So if we work our way down and find the right answer, we can stop. A says the emission spectrum of hydrogen contains a continuum of colors. That's false. We know that. It's a line spectrum. The visible spectrum has 4 lines in it. There's an ultraviolet range spectrum, and then there's an IR range spectrum. That's also the consequence of other transitions. So A is false. We don't have to go any further. 22. Which of the following statements best describes the Heisenberg uncertainty principle? Remember that one? It looks at any particle, the deviance from a position. If it's a very, very small deviation from a position, then you essentially know where it's at. Times the deviation of its momentum, which is mass times velocity, and we're talking about a change in velocity since the mass of the particles doesn't change. So we're talking about energy versus position. Has to be greater than or equal to Planck's constant over 4 pi. So that's the mathematical expression, but here we're looking at how is it in words, in prose? Well, it just says that you can't know both the precise location and the energy of a small particle. How about C? That looks like it fits. It's impossible to accurately know both the exact location and the momentum of a particle. This is momentum. That's the Greek letter rho. Okay. Ooh, we're getting into some electronic structures here. Okay. 25. How many F orbitals have the value n equals 3? Okay, n equals 3. Principal quantum number. The magnetic, no, not the magnetic, the angular momentum quantum number. Then we could either have a 0, a 1, or a 2. So it's S, P, D. There are no Fs. So the answer is 0. You don't have any F orbitals with n equals 3. N has to equal 4 before you get into Fs. Kind of a trick question. 26. How many F orbitals have n equals 6? Okay, n equals 6. 6. L can be 0, 1, 2, 3, 4, 5. So this is F right here. So that F then will go, M sub L would be -3, -2, -1, 0, +1, +2, +3. 1, 2, 3, 4, 5, 6, 7 orbitals. Remember, this is a shell. This is a subshell. And these are orbitals. So the answer is 7. You can have 7 orbitals. In fact, you can have, for any n 4 or larger, you can have 7 F orbitals. So if we're including everything above, say 4, 5, and 6, that would be 21 F orbitals, right? 7 each. 27. I better erase some of these. 7. If n equals 2, how many orbitals are possible? For everything under n equals 2. All right, so this is 0 and 1. M sub L equals just 1 for this one, and -1, 0, +1 for this one is 1, 2, 3, 4. Right. 4 orbitals are possible under n equals 2. Okay. 28. Roll a little bit. I think this one's starting to get weak on me. A given set of p orbitals consists of set of p orbitals exists. Well, p, if L equals SP1, that's a p. And then m sub L orbitals would be -1, 0, +1. So you have three orbitals in a p subshell. And we usually, for convenience, we usually call them X, Y, and Z. 29.
So I sent to you that chart I was talking about,
Uh-huh.
posted by Purdue. Like diagrams and small charts listing all the layers and how many.
Okay. Good, that works for you. Which of the following, I'm on 29, right? Yeah, 29. Which of the following is an incorrect designation of an atomic orbital? 29. So we've got E, E. Okay, we've got 1s, 3d, 1p, 4f, and 6s. S can occur for any principal quantum number. 1s is good, 6s is good. We just proved that 4f was the first principal quantum number that could have an f. That's good. 3d. So 3 is n, and then you could have a 0, a 1, or a 2, an S, P, or a D. That's good. This one cannot happen. You can't have a p orbital with n equals 1. All you can have is an S. That's it. So C is the bad one. Let's see, 31. A point in the wave function where the amplitude is 0 defines, all right, this is just memorized. That point where you have amplitude of 0, which means you're not going to find an electron there. That's a node. That's A. By definition. How many electrons in an atom can have the quantum numbers n equals 3, L equals 2? N equals 3, L equals 2. All right, so M sub L could be -2, -1, 0, +1, +2. And then M sub S could be a +1/2 or a -1/2. So 2 for each one of these would be 10. You'd have 10 electrons there. Okay. 33. How many electrons can be described by the quantum numbers n equals 3, L equals 3, M sub L equals 1? We only need to focus on this one. If M sub L is 1, then the only thing you have left is M sub S, and that's just 2. So 2 electrons. Oh, excuse me. Trick question. It is a trick question. If n equals 3, can L equal 3?
No.
No. No electrons. I trap myself with that one every time.
I can only get to 3 on and 4. So it can't happen.
Right. Yeah, that was a trick question and I caught myself. 34. What's the L quantum number for a 4s orbital? Well, L is SPD is 0, 1, 2. So the number L for s orbital is 0. Okay. 37. Which of the following combinations of quantum numbers do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? Which combination of quantum numbers is not allowed? Okay. So if we look at A, B, C, D, and E, yeah, E says all. All are allowed. Which means if we find one that's not allowed, then E has to be false too. So N, L, M sub L, and M sub S. All right. 9866. And then 8, 2 minus 5, 5. 8, 2 minus 5, 5. And then minus 4, 2 minus 1. And minus 5. And then halves all the way down. So we know that's permissible. Can L's be minus? No, never. So we got this one out. All right, that one's false. We found one that's false, so they all can't be allowed. Right, and we don't have 2 of the above or none of the above. We found the right one. Simply by knowing that L can never be negative. It's just N minus 1 is the maximum. Starting with 0. Let's see. How about 40? Who was the first chemist to recognize patterns in chemical properties of the elements? The temptation is to give it to Mendeleev, but he wasn't the first. No, it was, remember the triads? Those were similar patterns of chemical properties. That was proposed by Dobereiner. He had like the fluorine, chlorine, bromine, or chlorine, bromine, iodine, I think was his choice. And then he had others like lithium, sodium, potassium, and a couple of others. He just noticed that those three, each three group had similar properties. All right, 41. Mendeleev is given most credit for the concept of the periodic table of the elements because, remember why? Mendeleev, when he put his table together, he was putting it together based upon groups. Elements that shared chemical and physical properties. And he noticed that there were gaps in his table, because if he lined them up so that they only had similar properties, then he had to move some of them over, because in sequence of mass, they wouldn't fit with his scheme. So he left blanks. And he didn't just leave the blanks. He actually predicted the characteristics of the element that would be found there at some time. And sure enough, they were found and he gets the lion's share of the credit. So B is the best answer. He predicted the existence of unknown elements. 44. That's something that Julius Lothar Meyer didn't do with his table. The complete electronic configuration of 10 is, okay, to start with 10, we need to know how many electrons in the neutral atom. And from here, it looks like 50. Okay. So the order, we from left to right, put energy order of, I'm gonna have to erase some of this. The energy order of the orbitals. Actually subshells. And we would go 1s, 2s, 2p, 3s, 3p, 4s. Then we drop back down to 3, pick up a D. And then we go back to 4p. Then we get to 5s and 5s, and then we go to 4d and then 5p. And we may not need all of those, but you can derive these from the periodic table, right? 1s1 would be hydrogen. 1s2 would be helium. Then we add 2s1 would be lithium. 2s2 would be beryllium. And we just keep going. Right? So we got 50 here. We need, each S's can hold 2 electrons. P's can hold 6 electrons. Okay, because they have the orbitals -1, 0, and +1. And then the S again with 2, we have 6 here. Let's see how far we got. 4, that's 10, 18. Okay, 2 more. D's, how many can we put in D's? Just count across the transition elements. From scandium to zinc, there are 10 of them. That means you can have 10 electrons in the D's. Okay, and 6 here. Let's see. I've got 10, 10 more, 10 more, that's 30. 30 up to here. And then 6, 2, and let's see, that's 38. How many we got left? 14, 12? Yeah, 12 more. So if we put 10 there and 2 here, that should finish it off. And if you look at 10 on the periodic table, it's 2 steps into the P section. Right? The boron group starts the P's with P1s. The next group, the carbon group, has the P2s. And we're on the 5th period. So 5p2 confirms. Okay, so now we need to find out which one's which. We need a 5p2. A, C, and D are good. If we back up 1, we should find a 4d10. And the only one that fits that is D. I'm just using test-taking techniques. You know, save yourself some time with multiple choice questions. That's the quickest way to do it. Now, if we were doing this in abbreviated format, what would we do? We'd say 10, go backwards till you get to the 4th period, kryptons. 36. That would be the core. Anything beyond that. So if this is 30 and this is 6, then we would have 5s2, 4d10, 5p2. And that would be abbreviated format for this. But it asks for the complete configuration, so we kind of have to do it. 46. The statement that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals. Remember what degenerate orbitals are? I don't know if I mentioned that in class. It's one of the answers in your crossword puzzle, degenerate. Degenerate means that these orbitals have the same energy. So if you have a set of p orbitals, these, those are degenerate. They have the same energy. Okay. So the rule that says we try to maximize the number of unpaired electrons in here is Hund's rule, which would be B. Remember, if you've got 3 electrons, you put them in here like this. If you have 4, then you can start pairing them up. But we put the maximum number of unpaired electrons in the orbitals of a subshell. 47. Okay. This one looks familiar. 47. We got krypton with 5s2, 4d10, and 5p2. That's 10, right? We just did that one. So which one of these sections of the periodic table would 10 occupy? Well, 10 is a metal. It's to the left of that zigzag line. Yeah, it's just a metal, right? There's no other possibility. It's not transition. It's not a non-metal. It's not lanthanide or actinide. It's just a metal. So C is the answer to that one. 48 gives us a different one. So 48 starts at xenon, and then it works down to 6s2, and then it goes to 4f14. Yep. And then once it gets there, it goes 5d7. All right. 1, lanthanum, hafnium, tantalum, tungsten, 1, 2, 3, 4, rhenium, 5, osmium, 6, and iridium, 7. So even if we're off by 1, either way, we're still a transition element. I think it's iridium. Yeah, I'm pretty sure it's iridium. Let's see. Oh, we've got the configurations right there. 5d7. Yeah. 5d7. But those are in the wrong order. It's got 6s on the end. (49) All alkaline earths have the following number of valence electrons. Where are the alkaline earths? Second column over from the left. You're still in the S section. You're filling S orbitals, and you only have 2 electrons there. So they all have 2 valence electrons. That's why when you make an ion out of an alkaline earth, you get a 2+ ion. Calcium chloride would be CaCl2. 50. Titanium has how many electrons in its d orbitals? All right, let's see. 50. I smell trick question. So let's be real careful. Titanium. 22. No, not a trick question. How many electrons in its d orbitals? Well, it's the first instance of d's. Titanium is 3d, 3d2. There are only 2 electrons. So that's B. If we move down, say we went down to, say, barium, right? It would have in its core 3 Ds, 4 Ds. So it would have 20 d electrons. That's the kind of trick question that I'm looking for. How about iron? What are we gonna do with iron? Okay. What time did we start? 1:30? Okay, I've been going for an hour, right? Yeah, okay. Iron has a number of electrons that are unpaired in its d orbitals. Okay. So iron is 26. All right, so we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and it should be 1, 2, 3, 4, 5, 6 in the D's. Let's see if we got the right number. 4 plus 6 is 10. 4 plus 6 is 10. That's 26. Okay. So how many orbitals can we have in the D subshell? 2, 3, 4, 5. Because D's are L equals 2. -2, -1, 0, +1, +2. We have 5 in here. So let's put them in according to Hund's rule. 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4 unpaired electrons in iron's d orbitals. Okay. All right. We need to look at this chart and answer questions 53 and 54. All right. Which of the following represents the ground state for nitrogen? Okay. Nitrogen is 7. So we have 1s2, 2s2, 2p3, right? Well, it looks like that example gives us orbitals also, but it leaves out the 1s, right? So it leaves out the core. It's only interested in the valence. We have 1 here like that, like that. We have 3 here like that. So it's 2 and 3 unpaired. It looks like A would work for that one. How about N minus ion? How do you make that? You add an electron. Where does it go? Right there. So it's 2, 2, and 1, 1. So E would be the best answer for that one. 55. We're going to look at trends, are we? Maybe. In which group do, oh, no. In which group do all the elements have the same number of valence electrons? Really, all you need to do is look at where they're located in the periodic table, and they have to be in the same column. So phosphorus and sulfur are in the same period, not the same column. So A's out. How about B? Silver, cadmium, argon. Well, argon's a noble gas, so you know it's not going to match up. How about C? Sodium, calcium. Sodium's an alkaline metal, calcium's an alkaline earth. Can't do it. All right. D. Phosphorus, arsenic, and selenium. Phosphorus and arsenic, good. But selenium is in the same period as arsenic, not the same group. So it's out too. That means none of them. None of them have the same number of valence electrons in all examples. 58. The following elements, which has occupied d orbitals in its ground state neutral atoms? occupied d orbitals. All right, so if we're going to have d orbitals, the minimum atomic number is 21. You got to have 21 or higher, because 21 is scandium. That's where the first D's start. So for 3D, that means Z has to be 21 or greater. Okay, so let's look at our possibilities. Barium, yeah, barium's 56. Barium works. It has electrons in d orbitals. Calcium, nope, calcium is just shy. Silicon has 14, right? So it won't work. Phosphorus has 15. It won't work. And chlorine has 17. It won't work. They don't have enough electrons. Right. So the only one that works is barium. It has electrons in d orbitals. Of the following elements, which needs 3 electrons to complete its valence shell? The best way to approach this type of problem, 59. If you need 3 electrons added to complete your valence shell, look at noble gases, because they're all core. They're all completed shells. And take any one of those and back up 3 positions. Like neon would be nitrogen. And argon would be phosphorus. And krypton would be arsenic. Let's keep going. Xenon would be antimony. And radon would be bismuth. So any one of those requires 3 electrons to complete its shell. So which one do we have available? 59. Barium, calcium, silicon. Calcium, silicon. Phosphorus, chlorine. Phosphorus, here we go. Phosphorus, D. That needs 3 electrons to complete its shell. So it can look like a noble gas, electronically speaking. '62. Which of the following atoms has 3 wait a minute. 3 electrons in p orbitals in its valence shell. Oh, we need 3 orbitals in its 3 in its p's. Well, if the p's start filling with boron, aluminum, gallium, and indium, we would just need to say, all right, if they have 3 electrons, it would be boron, calcium, nitrogen. It'd be nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, so gallium. No. Name bismuth. There it is. Bismuth, D. That has 3 electrons in its p shell. And all you need to know is how the periodic table is structured. I answer those questions. '66. Which of the following is the highest energy orbital for a silicon atom? The highest energy orbital for silicon. Okay, let's see. Silicon is 14. It's in 3. So 3, highest in is 3s, 3p. 3p is the highest subshell. Highest energy orbital. Well, 3p. Actually, that's the highest subshell, not the highest orbital. The orbitals are degenerate, so any one of those would work, right? X, Y, or Z. So it's kind of a wording problem. But the best answer is D. Let's see, 67, right? So which of the following represents the ionization energy of bromine? Remember how to write ionization energy. You start with a neutral atom. If it happens to be diatomic, like oxygen or nitrogen, you got to split them apart. You got to get the atom in gaseous form. It has to be a gas state because you don't want to measure energy that's required to turn it from a liquid to a gas. You want to measure the amount of energy it takes to kick that electron out. So it's got to be in a gas first. And then the result of adding energy to it is a singly charged gaseous atom and the free electron. Okay? So C is the best answer for that one. 68. Order the elements sulfur, chlorine, and fluorine. In order of increasing ionization energy. Well, we know the trend, ionization energy. Right, if we draw our sort of our schematic here. There's hydrogen, there's helium. And ionization energy is increasing from lower left to upper right, or within a period from left to right, and within a group from bottom to top. So if we put these in order, we just need to say what's their relative position. Well, sulfur's down to the left of fluorine and to the left of chlorine. So this is the correct order. Increasing ionization energy. Fluorine is the most, chlorine is next in this group, and sulfur is last. Okay. 69. Uses the same set, doesn't it? Yeah, only this time we're talking about atomic radius. So what's the trend for atomic radius? Well, it works pretty good for the representative elements here, this, here, and here. And as we go from lower to left to upper right, we decrease radius. Okay. So that tells me that the order should be reversed. Now, in a period, the reason you get a decrease in radius is because you're essentially the same orbital structure, but you've got more nuclear charge, more protons, pulling all those electrons. The trend here is that as you go down, you're adding more levels, and that makes your atom bigger. And then the inner layers shield the outer layers from that nuclear charge. As you got these electrons here in the core, kind of protecting the outer electrons, so they can kind of do this thing. All right. This 69. Okay. Let's see, who else do we want to look at? 73. Of the following elements, which has the lowest first ionization energy? All right, all we have to do is just find out which one is to the right and up. So if we have barium is down here, right? Calcium is up here. I think it's right next to, yeah, right there. Calcium's there. Silicon is over here under carbon. And phosphorus is right next to silicon. And then chlorine is over here. Well, that's not exactly right. Chlorine's right here. These are noble gases. Okay, we got sulfur stuck in here just as a placeholder. But the one with the lowest first ionization energy is the one to the down and to the left. That would be barium. Lowest first ionization energy. That would be A. Of that same list of elements, yeah, 74. So this was barium. 74, got a different question? Which is most likely to form a negative ion with charge of 1 minus? Well, that's got to be a halogen, right? That's chlorine. Because it only needs 1 electron to fill its orbitals and to look like argon. So that would make it a -1. That's why all the halogens form -1 charges. That's chlorine. 75. Which of the following atoms has the largest ionization energy? Okay, the largest ionization energy would be we would be looking at this region up here if they're available. Oxygen would be right over sulfur right here. Lithium would be here, right? And neon, oh, that's a no-brainer. When you've got a noble gas, it will have the highest first ionization energy because it's removing electrons from its core. It doesn't have any valence electrons, right? It's all core. So neon would have the highest first ionization energy out of all of those.
Only competition being.
Yeah. And I'm not even sure that. I'd have to look that up. That's a good question. Does helium really have the highest first ionization energy? And it's got 2 protons and 2 electrons and no shielding. Yeah, it probably is. All right, 77. We're going back to wavelengths. We're regressing. Which has these types of electromagnetic radiation arranged in order of decreasing frequency? Okay. So if the frequency is decreasing, that means the wavelength is increasing and the energy is decreasing. Just to get things in perspective. For decreasing frequency, we want decreasing energy. So we want the order of decreasing, we want the last one to be the longest wavelength. Decreasing frequency, right? Yeah, decreasing frequency, which means less energy. So the first one, X-ray, is the highest energy you can get. So that's not it. We want, yeah,
These don't work because they're jumping back and forth with how long the wavelengths are.
right. It's completely out of order. Yeah. Radio, visible, ultraviolet, that's going the wrong direction. That's increasing frequency. Ultraviolet, visible. Oh, I erased it. Ultraviolet, visible, infrared. Yeah, that's decreasing frequency. Yeah, C is a good answer. Uh, 78. Which has these types of electromagnetic radiation range in order of increasing wavelength. Well, that's the same thing. Decreasing frequency, they're inversely proportional. So C is the answer for both of them. Kind of a trick, I think. See if you're paying attention. How about arranged in order of decreasing energy? Let's see again. Right. We have decreasing frequency, we have decreasing energy. And 80, okay. We're switching off now. 80. Starting to get weak too. In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property? All right, the principal quantum number is associated with what? Energy, right? Energy and size. The angular momentum quantum number is associated with energy, size, and shape. The magnetic quantum number is orientation. And then spin is obvious. So orientation is the answer to 80. 81, the angular momentum is shape. So this is 80 here. This is 81 there. Okay, how about 84? Select the correct electronic configuration for copper. And it looks like we can use the abbreviated form. Copper is 29. So if we back up, just go back up 28, 27, 26, 19. Argon is the next available core. So then we go from argon and we say, all right, we're down to the fourth period. 4s2 takes us to calcium. Right. And then copper is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here's the problem. I think I mentioned some time ago that there are some anomalies in the periodic table. And this is one of them. If we have 9 here, 2, 3, 4, 5, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. The lowest energy for copper is not this form, It likes, if possible, to have complete orbitals or half complete. So since we don't have half complete, we need another electron here. And where do we get it? We steal it from the s orbital. Okay. Well, that's what it would look like. 4s1 3d10 is copper. So B is the answer. I think that's why I put that one in there so that I could show you one of the anomalies. Now there's another anomaly in the 3D row. It's chromium. The chromium would be 24. And it would also have a core of argon. But it would have 4s and 3d. 18 from that is 6, right? So it'd be 2 plus 4. If we did that, then we would be one short of a half-filled D. It's more stable to take one of these and put it right here. So this would be 3D5 and 4S1. That's chromium. There are others, but those are the easiest to explain. All right. 85. That's not always the case. I checked. Some of them where you would think you'd see an anomaly, you don't. And it all has to do with solving those Schrodinger equations with the quantum numbers to give you the projected energies for the system. It's not like we've got some magic wand or some crystal ball that tells us. I mean, if it works with the formula, then that's the explanation. 85. Let's see, which of the following equation correctly represents the process involved in electron affinity for X? So this is going to be any element X. Again, we start with monatomic gas. And electron affinity means how attractive is it to electrons? So the electron this time goes on this side and it produces this gas with a -1 charge. And since this electron is coming from infinity down to the ground state, well, the outermost available orbital, it's going to give up energy. Okay, so remember our convention, when energy leaves the system, it's a negative sign. When it's added to the system, it's a positive sign. So this energy value is going to be probably a delta H, and it's going to be negative. So the larger, that sounds contradictory, the larger negative number, the larger value with a negative sign is the stronger attractant for electrons, the highest affinity. And in our chart, that would be fluorine. Okay, so to answer the question, that's C. '86 coming up. Which of the following lists of atoms are arranged in order of decreasing? Let's see, I got this thing's in my way. Move it. It won't move. There it goes. Decreasing atomic radius. All right, let's see. What do we have to work with? Lithium, oxygen, nitrogen, fluorine. Lithium, oxygen, nitrogen, fluorine. Sodium, strontium. Add those. Sodium and strontium. Already got fluorine and oxygen. And then calcium, cesium, sulfur, and selenium. Calcium, cesium, sulfur, and selenium. Okay. All right, we want the order of decreasing atomic radius. So that would be lower left to upper right, according to our picture. So let's nail down the extremes. The smallest radius would be fluorine. In order of decreasing, right? Yes, decreasing. So that's the smallest one. The largest one would be something down in the lower cesium. Would be the biggest one. And then let's see, looks like strontium comes in next, doesn't it? So we got this one, this one's gone. We could work our way back. We've got oxygen right next to fluorine. Okay. And then nitrogen next to oxygen. Uh-huh. Okay. And then what's next to nitrogen? Carbon. There's no carbon in there. Is there? No carbon. Okay. Sulfur is below oxygen and nitrogen. So I would say sulfur would, wait a minute, right, we don't have lithium, beryllium, boron, or carbon in there. So we got to come down one. So sulfur would be next because now we're adding another period, another layer. So sulfur, unless I missed one. Sulfur, phosphorus, silicon, nope. Aluminum, magnesium, sodium. We're staying in periods. Because if you go down one, you're ballooning your size. What's left? Calcium and lithium. Oh, I forgot lithium. Lithium ought to come in here. Lithium, then sulfur, yeah, then sulfur. Phosphorus, silicon, no silicon. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 6, 7. Oh, 8. So I left one out. Sodium. I put sodium in there. It would be, yeah, sodium would be here. Okay. And then come down is, I have to move these over. Come down would be selenium would be next in our list. Selenium. Yeah, then all the way over to calcium is next. That's it, except for I erased the strontium and the cesium. So that should be the order of size, and we just have to find out which one of these matches. What do we have in here that looks like that? Lithium, nitrogen, oxygen, fluorine. That's B, isn't it? That works. Yeah.
The way I'd see it is if I were looking at the question and I was figuring it out by looking at the periodic table, I'd see that C, D, and E are not in the right order. So it's either A or B. I would just figure it out from there.
Sure.
They come up with B.
Okay.
Because you'd see those 4 elements.
That's faster. Okay. All right. Moving on. 87. And I erased it already. I think we need the Broglie's equation for 87. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus third picometers. Which element is this? Okay. If the velocity is 1% of the speed of light, and the speed of light is 2.9979 times 10 to the 8 meters per second, 1% of that, we just reduce it by a factor of 100, right? 6. Tens, hundreds, 7, 6. So we know the velocity. We also know the wavelength. The de Broglie wavelength is 1.46 times 10 to the minus 3 and to the minus 3 picometers. That needs to be in meters, I'm pretty sure. So what's pico? Nano is 10 to the minus 9th. pico is minus 12. So this would be times 10 to the minus 3 times 10 to the minus 12. That, or 1.46 times 10 to the minus 15 meters. Okay, got that wavelength. And now we want to find out which element it is. All right, the equation for de Broglie was, see if I can remember it. I might have to derive it again. So this is the modified Einstein's equation at that. And then Planck's equation is this, which is equal to this, that over wavelength. But we're talking about a different velocity. So in this case, we've got to change that to v. Okay. So now these are equal to that one. Then we solve for wavelength, pull the wavelength over here. Let's see. You know what? I don't want to solve for wavelength. I want to solve for mass, because this is the de Broglie wavelength for one atom. If I know the mass of that atom, then I can calculate the molar mass. So let's solve for mass. Mass equals h velocity over lambda velocity squared. Right? Keep this one here, put this one over there, lambda velocity and h velocity there. So this one cancels, that one's gone. So this is h over lambda velocity. Okay, so now if I want to find the mass, I say Planck's constant, 6.626 times 10 to the minus 34 seconds, divided by this wavelength in meters, 6 times 10 to the minus 15 meters. And then the velocity, 2.9979 times 10 to the 6th meters per second. There we go. So that's the mass of one atom. Two point nine nine seven nine. So I guess 1.5164 times 10 to the minus 25 kilograms. Right, this is SI units, so that has to be in kilograms per atom. Okay, so now we can take this. Say we got to convert this to grams. Grams per mole is molar mass. So we convert this to grams first. 1 kilogram is 1,000 grams. Oops. Pick up, Dave. And third grams, 1 kilogram. There we go. Now they cancel. All right, now the atom. We want it per mole. We know the magic number for that. 6.022 times 10 to the 23rd atoms per mole. All right, so I already got this one in my calculator. I'm going to multiply it by 1,000 and then multiply it by Avogadro's number. And I get 91.2 grams per mole. So what would that be? Zirconium. Okay? That's how it's done. I think your textbook actually has the de Broglie equation derived and it's sitting there. But if you forget, that's how you do it. Let's see how we're doing. Running out of time. 88. In an investigation of the electron absorption spectrum of a particular element, it's found that a photon having 500 nanometers wavelength provides just enough energy to promote an electron from the second quantum level to the third. From this information, we can deduce. Okay, so we've got an electron moving from here to here. That means energy has to come in at 500 nanometers wavelength. Okay, A says the energy, you cannot determine from this wavelength the energies of the individual levels. You can only determine the difference in energy. Okay, so A and B can't be it. The sum of the energies? No, it's a difference in energies. So you can find out the difference in energies between 2 and 3. Now we can calculate for the Bohr atom, we can calculate the energies of each level with that equation, which I can't remember the constant involved, but it has some constant value. Okay, whatever that is. And then times, and we have the Z squared over N squared. So whatever that K value is that I can't remember. We can calculate the energy for each of the level using this equation. And then the difference in energies would just be one minus the other. Speaking of which, 89. So in the hydrogen spectrum, what is the wavelength of light associated with n equals 3 to n minus 1 electron, n equals 1 electron transition? So if we're going from 3 to 1, it's going to give up a photon. And actually, all you need is the absolute value of the energy transition. So if we're going from 3 to 1, we would say 3 is minus 0.2420. Actually, that's the final. It's final minus initial. Final would be 1, minus 2.17, minus 2.178 times 10 to the minus 18. And then minus, a minus, it was from 3 to 1, 0.2420 times 10 to the minus 18. Okay, so really you just need to say this one plus that one because there's a minus of a minus. 0.2420. So 0, 6, 3, 2 from 11 is 9, 1.9 times 10 to the minus 18. If we're going to use Planck's equation, it doesn't matter this part. It only matters the absolute value because it's either going to be absorbed or given up for the transition. So Planck's equation, we're looking for wavelength. So we need speed of light times, excuse me, not speed of light yet. Planck's constant first, then speed of light over wavelength. So if I move the wavelength over here and put the energy over here, now we can solve our equation. 6.626 times 10 to the minus 34 joule seconds, and 2.9979 times 10 to the 8th meters per second divided by this energy transition, 1.9360 times 10 to the minus 18th joules. And that will give us the wavelength in meters, 1.03 times 10 to the minus 7. Okay. So how many nanometers would that be? Well, we need to move it from 10 to the minus 9. So 10 to the minus 7 would give us 1.03. But if we moved to 2 more, that would give us 103. So 103 nanometers, if you need that unit of measure. What's the wavelength of light that's emitted when an excited electron of hydrogen falls from N5 to N1? You do the same thing. You say the final minus initial. So 1 is minus 2.178 and minus a minus 5.08712 times 10 to the minus 8. And just plug it into that formula again, and you should get 9.5 times 10 to the minus 8 meters. So the bigger the jump, the smaller the wavelength. Right? We went from 10 to the minus 7th in the first one with a 3 to 1 jump. And then from a 5 to 1 jump, we have more energy. We went to 10 to the minus 8th. It wasn't a big difference, but it's measurable. I'm not going to do that one just to save time. See. Got 15 minutes. Which of the following statements is or are true? 93. Okay. 1 through 5. Which ones are true? An excited atom can return to its ground state by absorbing electromagnetic radiation. It's the other way around. So that was false. The energy of an atom is increased when electromagnetic radiation is emitted. No, it decreases. We got to conserve energy. If it gives up energy, the energy of the atom has to decrease. The energy of electromagnetic radiation increases as its frequency increases. Yes. Planck showed that one. An electron in the n equals 4 state in a hydrogen atom can go to the n equals 2 state by emitting electromagnetic radiation of an appropriate frequency. Yeah, it's going from higher to lower, it's going to give up energy. Right? So 4 is also true. And the frequency of wavelength of electromagnetic radiation inversely proportional to each other. Frequency and wavelength are inversely, yes. So 3, 4, and 5 are true. That would be D. 94. So you probably saw this in your website, different shapes of orbitals. So the p orbitals are kind of dumbbell shaped. Which of the following statements is true about this p orbital? Actually, we could say this about almost any orbital. The electrons move along the outer surface of the p orbital. No. Let's just shorten this story. The orbital representations are probabilities of where you may find an electron in that region. It doesn't move on the surface. It doesn't bounce around inside. That's just says this is where you're probably going to find the electron, and we don't know exactly where it is. So the electron movement cannot be exactly determined is the answer. That representation doesn't tell you exactly where the electron is, because we're more interested in energy rather than location. In accordance with Heisenberg's uncertainty principle. 95. How many electrons can be contained in all the orbitals with n equals 4? Okay. N equals 4. So we could have L equals 0, 1, 2, 3. M sub L equals, you can have a 0 here. You can have a 0. You can have, I always do that. -1, 0, +1. Or you could have a -2, -1, 0, +1, +2. Or you could have a -3, -2, -1, 0, +1, +2, +3. I think there's a formula for this. Right, if you know that n, then you plug it in your formula and it'll spit out the number of electrons, but this is reliable. And each one of these can have 2. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 times 2 is 32. 2 electrons each would be 32. So what would that be? 4. How would you get 4? 4 to 32.
Each layer, it goes 2, and then it adds 4 at 6, and then it adds 4 at 10, it adds 4 at 14. You
Yeah.
just sort of add those up.
Yeah.
So
There's a formula where you plug the n in and it gives you the total number. I don't remember what it is. Like
that's,
it would be 2n times 4. If we had 2n, let's see, 8. Be 8 times 4 is 32. Does that work? What would it be for 3? It would just be this group here. Throw that one out.
for N3, it would be 18.
18?
Yeah.
Okay, so 3 would be 6 times, no, it doesn't work. Never mind. Maybe it's in your book, but I've seen a formula before that gives you those values. Not that they're really important. I think it's more important to know how to construct the configuration than it is just to count electrons. Okay, 96. The small but important energy difference between 3s, 3p, and 3d orbitals is due mainly to the penetration effect. Remember where you get this is distance from the nucleus. This is energy. So 3d looks kind of like this. And then 3p kind of goes like this.
If you need anything, I'll be around.
And like that. And then 3s goes like this. Like that. So its biggest hump is at a higher energy than either of the D or the P. But it penetrates to closer to the nucleus. So that gives it a lower energy. So the penetration effect answers 96. 97, which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? 97. Well, the one that he knew nothing about, electron configuration. He had no clue about electron configurations at that time.
He was trying everything else.
Yeah, he was using masses, chemical behavior, physical properties. Yeah, he put the whole thing together with that information. So A would be the answer. Which of the following atoms or ions has 3 unpaired electrons? 98. 3 unpaired electrons? Well, nitrogen, phosphorus, arsenic would work, right? Because it has 3 orbitals. Then you would expect if there are only 3 electrons in that shell, then they would all be unpaired. But that may not be it. Our selection gives us nitrogen, which fits. Right? Nitrogen has 3p, 2p. 2p with 1 in each. Right? because it's in the second period and, oh, no, third period, excuse me. 3P. 3P, it's in the third period and it's 3 positions in from the first P, aluminum. Aluminum's 1, silicon's 2, and phosphorus is 3. Oxygen doesn't work, it's got 4. Aluminum doesn't work, it's only got 1. Sulfur has 2 extra ones, it looks like argon. And titanium has a complete P shell. So, no brainer. Nitrogen is it. 101. Okay. Why do I keep picking that one up? An element E has electron configuration with 5s2, 4d10, 2, 4d10, and 5p2 with, is it krypton? Yeah, krypton. So which element is that? Krypton, it would be, that's 10. We're back to 10 again. Okay, so what could possibly be the fluoride of 10? Well, if these 2 electrons are missing, that gives us a 2 plus, right? Which would be logical. But that would give us 10 and 2 fluorines. Is that one in there? Well, EF2, no, EF2 is not in there. The other way, since these are the valence electrons, it could also lose those 2. And if it did that, now it would be 4. And this would be 4. So is it EF4 in there? Yeah, B. So that would be your best choice. I think that's why we didn't offer EF2 in there, because it would be a toss-up between the 2. 10 can either be a 2 plus or a 4 plus ion. And you can see that on the chart. 104, which of the following atoms would have the largest second ionization energy? Okay. When you're looking for the highest second ionization energy, the first place I'd look is the second electron coming from the core? Right. If the second electron is coming from the core, that means the first electron has to be coming from the alkali metals, because that would take out 1 valence electron and then you'd be immediately into the core. So the only one that works there is sodium, right? The rest of them don't work for the second ionization energy. At least when we're saying which one is the largest. Once you get into the core, you're talking about massive amounts of energy required. Okay, I'm about to run out of time. How many more do I have to go? 107. Pretty close on it. Oh, okay. Maybe I can finish it up. We won't go too far into your lab time. So 107, which of the following concerning second ionization energies is true? We're comparing aluminum and magnesium. Okay. If we're looking at aluminum versus magnesium, the valence electrons for aluminum are 3s2 and 3p1. Right? And for magnesium, it's only 3s2. Okay. Second ionization energy. All right. Ionization energies increase to the right. So first ionization energies are going to be higher for aluminum than they are for magnesium. But also the second ionizations will be higher. Simply because aluminum has more protons. Right? It has a stronger nuclear charge. So we know that aluminum is going to be the higher second ionization energy, but we have to look at the answers in terms of which one explains it. So if we say aluminum is higher, it's only A or B. They're not equal. So it has to be A or B. Aluminum is higher than magnesium because the first one says magnesium wants to lose the second electron, so it's easier. That doesn't make any sense. None of them want to lose electrons. You have to add electrons to them. I mean, add energy. So B is probably it because the electrons are taken from the same energy level, but aluminum atoms has one more proton. That's it. Increased nuclear charge. Okay, 108. I think that's the last one. Now, in the work problems, I go into an insane calculation. I actually take the energies and compare the energies for this equation, but I think there's a quicker way to get there. Consider a planet where the temperature is so high that the ground state of an electron in hydrogen is N equals 4. What is the ratio of ionization energies for hydrogen on this planet compared to that on Earth? So for a hydrogen atom with one proton and one electron, and this is the Earth. And this, 1, 2, 3, 4. This is our exoplanet. Okay? So if we're going to infinity from here to here, which one's going to take the more energy? Earth. We're ratioing the ionization energy of, let's see, what is the ratio of the ionization energy for hydrogen on this planet compared to that of Earth? So we want the energy of the exoplanet, actually the change in energy, ratioed to the energy of Earth. Right? Okay. Takes more energy for this one. So our ratio is probably going to be less than 1. Okay. We know that to calculate this energy, we need that constant I was talking about, right? Which is the same for both of them. And it's actually a difference. So if we say, let me back up. Hold on a second. Change in energy is going to be the final. This is the energy at infinity. And the energy at infinity should be the same for both of them. That's final minus initial. So the energy of the exoplanet now is going to be 4. And this is going to be the energy of 1. Okay. Actually, it's not delta. These are absolute values. The energy at it. So if infinity is the same, we're only interested in the ratio of these two because the ratio of these two is 1 to 1. So if we fill in the values for this one, we have that constant. And then we have Z, which is 1, right? Because this is hydrogen. And then the N for this one is 4 squared. And this one is that constant that I can't remember. And this is 1 over 1 squared. Okay? So these cancel. And this ratio is 1 squared over 4 squared, or 1 over 16. The ratio of the energies is 1 to 16. See? I'm sorry?
So would you like to hear my take on it?
Sure.
I would refer back to the question where it talks about N4 and think about 32. But you don't see 32, you see 16. 16 is the biggest. So you think instead of 32, 16. And hydrogen's 1.
Where did 32 come from?
The table with all of the N1 to N4
Uh-huh.
and total number of electrons in each subshell.
Oh, well, it's only got one electron.
It's a bit.
Yeah. I'd stick with the energy diagram.
I'm jumping all over the place.
So if we had, say, maybe if this were 3, then you'd have 1 to 9. If this was 2, you'd have 1 to 4. Or if this is 5, you'd have 1 to 25. Okay. As an analogous problem. Okay, I think that's it. That's all the ones I selected.